Hello everyone, welcome to this video. My name is Amir Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to use Google Earth Engine platform for the downscaling process using machine learning algorithm. In the first step, we need to identify the region of interest. In this tutorial, I'm going to select the part of Iran, southwest of Iran, that is a central region for agricultural activities. As you know, the soil moisture product is very popular for agricultural studies. That's why using the drawing tools available, I'm gonna select a farmland as a main study area in this tutorial. For example, I'm selecting a region in the southwest of Iran that is one of the central regions for agricultural activities, and you can also choose wherever you want. It's no matter where you are working. This tutorial, the platform, and the data, all of them available globally, and you can use it for your own studies. So find a region as your study of, as your actually set a region as a region of interest using drawing tools, just like me. And then using map.center object, focus on the region of region of interest that you are selected. Map.center objects for geometry, helping us to have focus on the study area, as you can see here. So most of the users asking me about how to show the rest of the code, just like that. It is very simple technique that's helping you to speed up typing in your programming techniques. So for example, when you write a part of a code, for example, map here, if you press Ctrl space together, the rest of the code will be shown here. And then you can choose the code you want, and that's highly helping you to avoid syntax error in your programming. So, and now we need to call the soil moisture product, the SMAP soil moisture product, in which we want to improve their spatial resolution. Make a new variable as for the soil moisture, and then through the search places and dataset, type SMAP soil moisture. Soil moisture is one of the actually the SMAP is one of the well-known satellites for the soil moisture estimations. Each data available with 3 hours and daily temporal resolution with 9 kilometer spatial resolution. As you may know, climatological data and soil moisture data are highly suffering from the coarse spatial resolution. Specifically the soil moisture products, because there's SMAP satellite using actually the passive microwave data that needed coarse spatial resolution to gather microwave electromagnetic radiations that are emissions that's emitting from the Earth's surface. So that's why the spatial resolution in soil moisture data is a little lower than the other satellite sensors. So here, as you can see, the data is the near real-time data is available with 3 hours temporal frequency imported into the code as an image collection. Then assigning image collection to the SM variable, but there are various bounds in this product. Go to the data description to get more information about the data characteristic and also the temporal information and also the other things. So when I go here and also when I come here you can see that the spatial resolution in the bands mentioned 11 kilometer or 11,000 meter, but it doesn't matter because we want to improve its spatial resolution from 9 or 11 kilometer to 1 kilometer using modest products. Here there are various bands available here, but the target band is surface soil moisture data, that is top layer soil moisture from the surface to 5 centimeter below the surface, as you can see here. and also the data name and all information is available here. Just copy the target band and paste it into the code. As you can see, through the image collection, use .select to find the target band first. Then use the filter date to actually spans your data from a time start to time end. That filter date, two variables needed here. One of them time start and another one time end. Make time start just like that. Earth engine.date is a function for converting a string to date information or the date format. So from 2023, and the next variable is time and Earth engine dot date, helping us to define the string 2024 for the end date, and then import the time start and time end into the parentheses to span our data to a specific period of time we want to work in. So the soil moisture product is available, but it has 3 hours temporal frequency that is too much for our goal, because we want to reduce its temporal frequency first to 10 days interval, because the 10 days interval reduces the number of images for processing. That is very good to speed up processing steps, and also still it is enough for most of the applications in agricultural studies. So here I'm gonna convert this data from the 3 hours temporal frequency to the 10 days average. It's very simple technique. For the first step, we need to make a list for 1 year, including the date information with 10 days interval. So here a list with 10 days interval equals to Earth engine dot list dot sequence, including couple of arguments. The start value in the list will be 0 and the end value will be the difference between time end and time starts. Here, if I want to get the difference between time start and time end with the day unit and also 10 days interval, just I need to write time end dot difference time start. The difference and the date function helping us to calculate the temporal difference between time start and time end according to the number of the days, and with 10 days interval. Get rid of count at the end. So here we will have a list with 10 days interval, just including the numbers for each date, not the date information. Here we have a list starting from 0 with 10 days interval to 360 for the year, for the whole of the year. In the next step, I want to replace each one of these values with the date information for 1 year. To do this, we need to make a loop using .map. .map, make a new function, and now inside the function, each input value in the function considered as an I, and finally function returning Earth engine dot date dot from ymd, because we want to have date instead of the value in our list. That's why function returning the date format. For 2023, the date dot from ymd, including couple of arguments. The year equals to 2023, the months equals to 1, and also the day equals to 1. Skip time zone. So actually we want to calculate from January 2023, the first day, with 10 days interval in advance until the end of the year. That's why I'm using that advance to go further in the date information with 10 days interval from starting date. That advance, the delta is the 10 days difference that is already defined in our list, and the unit will be days, and skip the time zone. Now save your code and run it again. Again, we have a list with 37 elements that you can see starting from 2023 January to December 2023 with 10 days interval. The first day, the day 11, and the day 21, the day 31, the day 10, as you can see, with 10 days interval, we are going forward from starting to end for 2023. The list of the dates created. In the next step, I want to filter my data with 10 days interval and calculate the average of soil moisture for each 10 days. So make a new variable, soil moisture with 10 days interval equals to get a list of value, a list with 10 days interval, and use a map to make a function. For each row, as you can see, we have a list that including the start date for each input or for each image that is going to use for the temporal conversion. That's why we use the start date as an input argument in this function. The start date, then here first we need to convert the start date from a normal format to the date format. EarthEngine.date helping us to do this very well. So after the start date imported into the loop, as you can see already we had in the list, now imported into the loop. Now we need to calculate the one end date for each one of these inputs. Make a new variable as end date equals to from start date go forward using .advance with 10 days. 10 unit will be days interval. So now the time end calculated with based on each time start. So for the next step, the final image the final image is going to calculate based on this start and end date. So, and here we will have the soil moisture product just like that. That filter date again based on new start date and new end date, just like that. Finally, get the average for us using .min. The code returning the final image, but the final image needs to have new system time start and new system time end, because it is an average of 10 days based on new start date and the new end date, and also it doesn't have the 3 hours interval anymore. That's why I'm setting a new properties using .set system time start equals to the start date or new date information with millisecond format. As I mentioned in the previous tutorials on my YouTube channel, the EarthEngine uses the millisecond format for time series analysis. That's why the start date and end date in the properties should be converted to millisecond formats. Then .set again for system time end, and this time end date with millisecond will be available. And also I will set a new system index according to the normal format for a start date. If you want to see the start date with the normal structure like year, month, and the day, you can use dot format. Dot format convert the date from to a string with year, month, and day format. The 10 days product is made now, and you can print and see how it works. Print soil moisture with 10 days. So with 10 days, the aim is run the code again. Again, we will have a list with 37 elements, but this time, instead of the dates, we will have one image that is an average for each 10 days we already had in the list 10 days. If you go to each date, you will have a surface temperature, surface soil moisture, and also it is available for one specific date, or that is available for a period of time that's already explained by system time start and system time end, and system index helping you to know that what is the system actually the time start for each date, for each image with the normal format. So the image collection created, but it is not an image collection. It has a list structure. We need to convert it from a list to image collection. Earth Engine.image collection simply helping us to do this conversion. Earth Engine.image collection, just like that. Run the code again. We will have one image collection now with 37 elements for 1 year. If I want to do the visualization, map.addLayer is a helpful function. Couple of arguments we have in the map.addLayer. Instead of the object, we will have soil moisture data with 10 days interval, and skip the visualization parameter. If you want to have all bands, you can stack them using .to bands into a single band, into a single image, and clip it based on the region of interest, and the layer name is soil moisture with 11 kilometer spatial resolution, and use the false for the shown argument because we want to avoid automatic visualization. So that because it highly reduces the speed of processing. Save your code and run it again. Then we will have focused on the study area. In the layers, soil moisture with 11 kilometer is available. Go to the layer setting and you can see the 10 days product is available. One of them is selected. Increase the visual actually contrast by a stretching technique, and click on apply to see the soil moisture variation in this image. You can use different techniques for the soil moisture visual. You can use different enhancement techniques available here. This is the soil moisture products that is calculated for the period of time. This technique for 10 days conversion is very helpful. You can also use different techniques such as the median technique, the average technique, or even getting maximum, minimum. You can use different statistical operator to produce the 10 days product. For example, if you use median, it is a helpful technique that avoid from some extreme values in averaging. That could be a good technique for the time series analysis. Now The product with 11 kilometer again is available. You can use increase the contrast by stretching techniques we have here, and even you can replace this product, the soil moisture 3 hours product, with other soil moisture products we have. For example, the next product is available with daily temporal resolution. If I go to the data description, you can see that the data is available for the soil moisture band and also with 9 kilometer spatial resolution. I can import it into the code, and instead of 3 hours data, even we can use these products. Nothing changed in the code but the band name. Go to the data description, and here the target band is soil moisture AM, and go to the data information to get more understanding about the bands and data characteristic. As you can see, this is the volume fracture for the soil moisture. Just copy and paste it into the code, the target band. Instead of the previous one, we will have a new band name here. It is pasted, and run the code. Nothing changed in the code but the image collection ID and the target band, and everything and also I keep everything same. And also here you can see a new 10 days products. It has a better quality because it has 10 days, because it has actually the daily temporal frequency. Using stretching techniques such as 90%, I can increase its visual characteristic, that you can see the white areas showing the higher moisture and the darker region showing the lower moisture value. So, and also we will have some no information or no data pixel in this product. That is typical because it will have no data for those regions that no soil moisture detected. That's why we will have no data in this product. So the original data with 9 kilometer imported and converted to 10 days temporal frequency. Now my target is call other products in the other products such as the NDVI, surface reflectance, and the temperature product to improve to modeling to modeling higher spatial detail for the soil moisture product. Before doing further, now I want to show the reference article I want to use for this tutorial. Last year I have published a paper as SMAP downscaling using MODIS product in the Google Earth Engine platform. This is the full name of the paper, and also I will add the paper's link into the description box on my YouTube channel below this video, and also you can use this as a reference for this tutorial if you want to use this code for your study actually. And also all the steps clearly described here, and also this is the whole flow chart we want to do the downscaling based on. We need to have the MODIS LSD surface reflectance data and also the NDVI and land cover products. These products combining into a single collection, and then we will use these products and soil moisture from SMAP into the modeling to predict the higher spatial resolution for the soil moisture data. So now in the first step, I need to call MODIS LSD product into the programming we are working on. So here, go to the search places and dataset and type MODIS temperature. MODIS temperature data is also available with 1 kilometer spatial resolution. This is a target spatial resolution for us, and also it has the daily temporal frequency, but we need to convert it to the 10 days interval. Import it into the code, and as you can see, it is available as a second image collection. Make a new variable as temperature equals to The second image collection, modest temperature data assigned to the temperature and spans the temperature data same as the soil moisture according to the time start and time end for 2023. Now we need to select the target bands here, but before that we need to go to the data description in the bands, and as you can see, one band is LSD day with 1 kilometer spatial resolution and it has 1 scale factor, and the second is LSD night with 1 kilometer and also 0.02 as a scale factor value. So now I want to select LSD day and LSD night. Select all the bands starting with LSD and the rest it doesn't matter, and now just print the temperature to see that how many products available for this period. 365 features available. In each image or in each feature, 2 bands as LSD day and LSD night is available. So, and also in addition to the LSD, if you're going further into the article, you will find an equation that shows the higher the soil moisture data is actually dependent on LSD day, the delta LSD between LSD night and day, and also the surface reflectance values in band number 5, 6, and 7, and NDVI images. These are the independent variables that we want to use them to predict higher soil moisture, the soil moisture image with higher spatial detail. So the LSD day is available, but for the delta LSD, if you go further, you will find the equation here, and also it is available in the chart. As you can see, the delta LSD equals to the subtraction between LSD day and LSD night. So back to the code here. For each date we have LSD day and LSD night, and now I want to convert it into the 10 days interval first, and then do the calculation for the different for the delta S and other variables we need. Let me to make a bigger space for the code, just like that. That is easier for you to follow the codes I'm writing here. A new variable we have with as temperature 10 days equals to, again we will have a list of dates as list 10 days dot map. This is the same as previous function we had for the soil moisture, but the only difference is about the import image for filtering based on system start date and end date. That's the only thing that makes the difference between the new 10-day product and the older one. So the input is start date, same as before, or even you can copy and paste it to increase speed of processing, to increase the speed of tutorial. So here, instead of soil moisture, we will have the temperature with 10 days equals to, in image collection format, we have a list including 10 days interval for 1 year, and also each start date equals to date format, and then the end date will be calculated based on 10 days difference with the start date in advance and also going forward. And then finally here, the image we want to filter it based on a start and end date. The new one will be the temperature. The temperature is the target image, and we can get a median for the period of time we have. So as you can see, now the median temperature or the mean temperature is available for each 10 days, and also finally the function returns the temperature data, as you can see here. But now in the next step, we want to select the LSD day and also the difference between LSD day and night. To do this, make two variables. The first is LSD date. From 10 days product, first select LSD day with 1 kilometer spatial resolution, and its scale factor will be 0.02, and then the LSD night equals to actually the temporal from the new collection, select LSD night with 1 kilometer dot multiply 0.02. So LSD night and day separated here. So to get to do the subtraction, LSD delta equals to get LSD day first and do the subtraction between day and night, just like that, and rename it as LSD delta or delta LSD. So finally, function returning LSD day and the band explaining the differences between difference temperature between day and night. Return LSD day dot add bands with a new band as LSD delta. Print the code temperature with 10 days interval. As you can see, again an image collection with 37 elements is available. For each date, we have one LSD day and one LSD delta that is calculated and well explained in the previous steps. So for the next step, we need to use NDVI product. If you go further in the article, in the main equation here, you can see that the soil moisture dependent on LSD day and also the delta LSD that is calculated. But the rest of the actually parameters that is necessary are surface reflectance bands in mid and shortwave infrared regions, and also the NDVI bands. To find these bands from MODIS products, we need to use MODIS surface reflectance product. Go back into your code and search for MODIS surface reflectance product. As you can see, the MODIS surface reflectance products with 1 kilometer and 500 meter spatial resolution is available. Imported into the code here as a third image collection. So the third image collection is available here, and now I'm making a new variable as SR. So the new SR, including the third image collection for the time start and time end already created. Time start and time end. Print surface reflectance data. In the right panel, you can see 365 elements is available. For each date, 22 bands is available, but the only bands we need, band number 4, 5, and 6, or let me to check it again, bands number 5, 6, and 7. We need these bands and also the NDVI. It is also very simple technique to select the target bands and calculate the NDVI. Back to the code first, and now I'm gonna make an equation to do this to calculate these parameters easily. But in the first step, we need to mask out the cloudy region from the images. But and also here we can use the temperature product or MODIS LSD product as a actually as a helpful product to mask out regions including a cloud cover, because already cloud covers excluded from the temperature product and also we can mask out the region covered by cloud according to the temperature product. For example, let me show you an example from the temperature product we have here, map.addLayer. For the temperature data that's limited, for example, we want to have the temperature data in a single stack layer that is clipped based on the geometry or region of interest, and also its name is temperature, and use the false at the end to avoid automatic visualization. Here just I want to show you how the cloud cover excluded from the temperature product. Run the code now. In the layer setting, as you can see, for example, one of the LSD days or LSD nights, no matter, just one of them for one date selected. And here you can see the regions excluded from the images because they are highly covered by the cloud cover. Or another date, for example here, in another date you will see that the other regions excluded from the image because these are covered by the cloud cover. It is very useful product that helping us to remove the cloud cover from the surface reflectance data, because both of them are daily and also both of them related to one single satellite sensor, and also we can combine them to exclude cloud cover from surface reflectance bands too. And also it is there is one scenario to use QA bands in the surface reflectance product to exclude the cloud cover from images, but it's a little reduces the speed of processing. That's why I'm gonna use the temperature product to mask the same regions in the surface reflectance data to exclude the cloud cover for the further processing in these bands. It is a very simple technique. Just I need to combine a surface reflectance product with the temperature product, because both of them for a same satellite coming from a same satellite sensors, and both of them are daily, and also that's why we can combine them easily here. Combine with temperature data, and now if I use the print for each date, we will have the temperature data and also the surface reflectance bands. Let me to select the surface reflectance. All the bands is starting with surface, just like that. Run the codes. Then you can see that 9 bands is available for each date. One of the LSD bands is enough, as we are working on day data, the day surface reflectance data. We need to skip the LSD night here. That's why I'm selecting LSD day with 1 kilometer. Again, here you will see that we have 7 bands with 1 LSD day. So it is good. Now we want to exclude the cloud cover using a very simple technique. Make a new function first as a map. Using the map, make a loop, and also inside a loop we will have a function, each input image considered as an IMG, the output including the surface reflectance bands, all the bands starting with SUR that are masked using update mask, that are masked based on the LSD data. Image.select the mask based on LSD image, and also this technique helping us to turn the surface reflectance cloudy pixels to no data value based on no data values we have in the LSD bands. And then I want to copy all properties of input images to the output. That's a very simple technique. Save your code and then finally you can visualize the surface reflectance bands for the period of time we are working, and its name is SR for the layer settings, and run the code to see what the result is. The surface reflectance product is available, as you can see. Cloudy region, all of them excluded. One random date selected. As you can see, the cloudy region already removed from the image. This region covered by snow. And also, for example, I can find another date randomly, just like this. And cloudy region, all of them excluded here. Yes, this is the simplest technique that we can use to get rid of cloud cover when you are working with a Modis product by combination of products. Even if you don't have QA state band, you can use the temperature data to exclude the cloud cover from the surface reflectance images. So after cloud cover removed, now we want to convert the surface reflectance to the actually 10 days product and get the maximum value for each pixel in NDVI images, and also get the average of surface reflectance for the 10 days. It is very simple technique, and here I can make a change here to actually calculate the NDVI and add it next to the other surface reflectance bands that we need for the modeling. For example, here I make a new variable as bands equals to, or mask the bands equals to the masking process here. Yes, and the mask bands including the surface reflectance bands that is excluded from the cloud cover. Now and also we need to apply the scale factor that they have. If you want to know about the scale factors, go to the data description in the bands, open it in the new page to get more understanding about the actually possible scale factors. And as you can see, we have a scale factors for these bands that should be multiplied on each input bands. Here that multiply the scale factor, and now we need to have the NDVI to calculate the NDVI, get masked bands first. That's normalized difference between band number 1 and band number 2. Band number 1 and band number 2. Actually, the band number 1 is the red, and band number 2 is near infrared. A normalization difference should be done based on near infrared and red region of electromagnetic spectrum. Rename it as NDVI. And finally, we need to have also the from surface reflectance, we need to have bands number 4, 5, 6, and 7. So finally, the function returning from masked bands dot select surface reflectance from band number 5 to 7 and dot add bands the NDVI. Yes, there is. And now we can get a print to see that if everything is okay or not. For each date, now we have one NDVI with other surface reflectance bands that is necessary for our calculation. So back to the article, and as you can see, the LSD day calculated, the delta LST is also calculated, and now we have the NDVI and other surface reflectance bands that is mentioned here. So for the next step, we want to do the modeling based on the random forest equation. But as you can see here in the charts, in addition to the NDVI, surface reflectance, and the LSD data, we want to have the modest land cover product too, because helping us to differentiate the different land covers and helping us to get rid of some of the classes that we don't want to have. So back to the code here, make a new variable for land cover. Land cover equals to, from search places and dataset, type modest land cover product. Here you can see modest land cover is available. Modest land cover yearly global with 500 meter spatial resolution. The one thing is important when you want to do the downscaling process, you will have one dependent variable. For example, here the soil moisture is a dependent variable, and you will have a couple of independent variables regarding to the soil moisture. For example, the temperature and also the surface reflectance, the NDVI, and also the land cover. These are the actually the independent variable that we're going to use for the modeling and also to predict the higher soil moisture with higher spatial resolution. An independent variable, the surface reflectance, temperature, the land cover, all of them must have the higher spatial resolution. For example, if the target resolution is 1 kilometer, all the independent variables should including 1 kilometer spatial resolution, or from 500 to 1 kilometer. It is very important in the downscaling process. For example, if your target resolution is 1 kilometer, you cannot use 2 kilometer product here, because the target resolution is 1 kilometer and we want to use 1 kilometer data or 500 meter data to model the higher spatial resolution. So, and the land cover equals to the modest land cover added as image collection number 4, and here image collection number 4 added to land cover variable, and I want to make a unique and integrated land cover for the whole period of time for my study area using that mode. Actually, the mode is a kind of a statistical operator helping me to get the most frequent classes and from start date to end date. And then I want to clip it based on the region of interest, but I can do it in the next step. There are a couple of land cover maps in the modest land cover product, but the most typical one is LC type 1. LC type 1 is the most typical layer that we use for the land cover mapping. So here the land cover is also ready. Now I want to make a unique collection that helping me to actually to integrate or combine all the independent and dependent and all independent variables into a single collection, and then I can do the modeling in the next step based on. The new collection or the final collection will be collection variable equals to, so for example, but I forget to convert the surface reflectance data to 10 days interval. Sorry, it was my mistake. I totally forgot it. And also here I just copy the temperature 10 days and paste it for the surface reflectance data easily with a little change. Here we will have SR with 10 days. We will have it into as an image collection. Then we are going to use the list of the dates with the 10-day interval here. Everything is same until here, but here instead of the temperature we will have a SR or surface reflectance. So now here I want to make a variable for NDVI equals to, from input SR select the NDVI bands and then filter it based on the start date and end date, and get the maximum NDVI values in each pixel. This is the maximum value composite that is a traditional way to actually recover the missed NDVI values, specifically in the agricultural areas. And then for the surface reflectance bands or the multispectral bands, I'm select all the bands starting with SUR, just like that, and then filter it based on start date and end date. So here we get just a median average for a period of time for 10 days, or here you can see, and then skip other calculations that is not relevant to the surface reflectance data. As you can see here, the maximum value and the average value for each 10 days for NDVI and multispectral bands is calculated, and finally the multispectral bands with NDVI will be returned just like that, and then print SR with 10 days. Run the code again and save it. We will have a new image collection with 10 days interval for NDVI and also the multispectral bands, and already cloud covers excluded thanks to the temperature bands we have. It's under calculation. It's a little time consuming. It is understandable because a large number of images and data are involving into process. 37 elements. In each date we will have multispectral bands and NDVI. So now back to the coding, and as you can see the land cover calculated. Now we want to make a single collection including all dependent and independent variables in the single image collection. So a new collection equals to, so first we will have the surface reflectance with 10 days that combine with temperature data with 10 days. As you can see here, this is the temperature collection with 10 days interval, and then also we have the soil moisture product with the 10 days interval. That's combine the soil moisture product, print collection, and save your code. In the right panel, we need to wait until collection created. Then I will show you in each date we will have an NDVI, multispectral bands, delta LSD, LSD day, and the soil moisture data. And also for the downscaling process, it is necessary to resample the soil moisture product from 10 kilometer or 9 kilometer to the target spatial resolution. For example, the target pixel size or spatial resolution is 1 kilometer. That's why I need to do a resampling for the soil moisture product to do the conversion from the original spatial resolution to the target pixel size. So dot resample and then dot reproject. Couple of arguments we have here. Instead of CRS is the coordinate system for the resampled image, that you can get the actually projection or coordinate system from each input image. Projection dot coordinate system coming from each input data, and also the scale will be the spatial resolution or the pixel size will be 1000 meter, and skip the rest of the variables and save the code now and run it again. So here, as you can see, for each date, the multispectral NDVI and also the LSDs with the soil moisture data is available. If you want to have the land cover product as a single band next to the others, it is very simple, but you cannot use the combine anymore. Just we need to make a loop and add the land cover as a new band next to the others for each date. Here, dot map, make a loop, each input image considered as an IMG, and function returning each IMG with a new band that is the land cover. Run the code, but remember to copy input properties for the outputs. As you can see, a new collection created that will include the LSD type 1 next to other bands. Remember to save your code. Now all the independent and dependent bands gathered together into a single collection. For the next step, I want to do the modeling process. As you can see, we have one single collection including 8 bands that all the dependent and independent variables available here. So now I want to make a loop to calculate or predict soil moisture with 1 kilometer spatial resolution for each date I have the soil moisture data. So as you can see here, a new variable is soil moisture with 1 kilometer equals to from collection, get all the images in the collection and bring them into a loop. Each image or each image in the collection, consider it as an IMG and do this calculation that I will show you for each one of them. So first, we need to collect the training sample for each date separately. A new variable as training data equals to from input image or from the IMG using a stratified random sampling, you can collect the samples automatically without manual structure. So couple of arguments are necessary here. If you want to see the arguments, just again you need press on control and space here. So the number of the points, the number of samples we want to have for the modeling process, the number of the points or number of samples for each soil moisture data is, for example, 10 samples. And when you can also set the larger number of points as samples for each soil moisture value, but remember that higher values will reduce the speed of processing. That's why I'm trying to use lower number of samples for each soil moisture value. So the class band is the band that I want to do sampling based on is the soil moisture band, like that, and the region of interest is the geometry I have defined earlier, and the scale will be the target scale, 1000 meter. These are the training data collected for each input images. Then I want to define a regression model that's going to be used for the prediction, for predicting higher spatial detail for the soil moisture. Now make a new variable as a model equals to earth engine.classifier several machine learning classifiers available in Google Earth Engine platform, and you can find one of them, and also you can choose every one of them, including regression format for this tutorial. For example, I'm gonna use the random forest dot classifier dot random forest, or smile random forest. Classifier dot smile random forest. As you can see, this is one of the most well-known advanced regression techniques in machine learning algorithm, that you can use it whether for as a classifier or for regression analysis. So the number of trees in this process could be something value between 50 to 100, and also experimentally I used 80 as the optimum number for the process. So, and then we need to train the model based on the training data. So, couple of arguments are necessary here. Sorry. Yes. For example, the input features, we want to train the model based on the input features. Let me to make a parenthesis like that. So the input features, we want to train the model based on input features. The input features equals to training data, not date. Sorry. Training data, and the class property equals to the soil moisture band, and the input properties including the band names. The input properties including the band names. From input image, extract the band names and set it as input properties, just like that. So the model is created, but now the model working as a classifier, because originally it is a classifier. If you want to turn it into the regression format, that sets output mode is a code that helping you to do this conversion. The output mode could be classifier or regression. Here I'm gonna use regression. Only some of the classifiers can work as a classifier and also as a regression technique. For example, cart, random forest, and also some other methods such as minimum distance working as a regression too. But if you want to use the support vector machine, at least in the Google Earth Engine, not possible. So the model is created, and now I want to apply the model on the independent variables to predict the dependent variable with higher spatial detail. So now the result equals to from input image, but in input images from input images we need exclude the dependent variable. Make band names equals to from input image get band names dot remove skip the soil moisture band. Now I'm selecting all independent variables with higher spatial resolution between 500 meter to 1000 meter, and then I'm applying the regression model using classify function, and the results renamed as SM with 1 kilometer with float format. And don't remember the input file, the soil moisture data, the dependent variable should have the integer type of value. So, but here we have a problem. Actually, the input image, as you can see into the if you go to the SMAP data description here in the bands, if you go to the bands, you can see that nothing mentioned about the range of the values. And also you need to check that how the range of values changes, because if the values changes from 0 to 1, you need to actually do a conversion. You need to convert it into the integer format with a coefficient, with the extra coefficients. So to get more understanding, here we have soil moisture data. For example, select one of them. For example, one soil moisture data, the original ones selected, and applied. As you can see, the visual characteristic is a little changed. You cannot see the pixel effects because it is resampled to 500 meter to 1000 meter, as I showed, actually as it is mentioned before. That's why the visually had a little change. And now if you want to see the range of values, just you need to do some sort of stretching, and as you can see, the values typically ranges from 0 to 1, and that's why we need to convert it from a float to integer format with an extra coefficient. So it is a very simple technique. For example, here let me to make a new variable for resampling, and then the img assigning the resampling assigning to the new variable, and finally the function returning resample image dot multiply to 100. I want to convert it into an integer format and also with a single coefficient, that is 100, and then use dot to integer to convert it from float to integer format. This is the way that you need to do a conversion between float to integer when the original values ranges from 0 to 1. And finally, when you want to get get the result in the original range of values, here you need to divide the final result to 100 and then use dot float to convert it from actually the integer to the original float range of values that we expected for the final result. So now the function returning the result with the properties of input images, the img system time start and system time end. This is the system time start and system time end, as you can see. And also for the further comparison and also the corrected term, and also for the final correction, we need to have the original soil moisture band next to the sharpened one. Dot add bands from input image dot select the original soil moisture image. I can also change the original name from soil moisture AM to soil moisture here SM with 9 kilometer, just like that. Print soil moisture SM with 1 kilometer. Save the code and run it again. So a new image collection will be created, including soil moisture with 1 kilometer and its original resolution with 9 kilometer. Maybe it's a little time consuming, because large number of images and data involved into processing, and as much as you select a larger area and also a larger number of the points, definitely the speed of processing will be decreased. And there is also one way to increase the speed of processing. For example, you can use this process using the other modeling techniques that are available that I will show you in the next step. Now you can see the model is run and soil moisture with 1 kilometer and 9 kilometer is ready. But now in the final step, we need to do a correction for the final output. The soil moisture now with 1 kilometer resolution, its value should be corrected based on the original image values. So here we will have a correction term here, but before that we need to get the average from the 1 kilometer data. Here the soil moisture 1 kilometer average equals to, from SM 1 kilometer, select the SM 1 kilometer band and calculate the average value in each pixel. Now for the correction, we will have from soil moisture with 1 kilometer, make a new function to add the correction term to each sharpened image. First make two different variables for 1 kilometer and 9 kilometer data. So here SM 1 kilometer, from input image select 1 kilometer data, and then from input image select 9 kilometer data. But as you remember, the 9 kilometer data has integer formats. We need to convert it to the float using .divide. We already did this process for the sharpened data, but for 9 kilometer data we should repeat it again. .divide to 100 and to float. So the correction term equals to each sharpened soil moisture add to differences between the 9 kilometer band and sharpened average. Subtract from sharpened average, and this will be final SM soil moisture 1 kilometer, that is final and corrected. Corrected is better here. Function returning the corrected soil moisture with properties of input images. Print SM core and save the code and run it again. In the right panel, the corrected soil moisture is under calculation, and same time here I will show you how to get export from the corrected soil moisture. It is very simple. If you followed my tutorials on YouTube channel, definitely you know that how to get export from input images. Export so here mentioned that SM 1 kilometer didn't match to anyone. Oh yes, it was something wrong here. Something is wrong here. Here we need to have SM like this to solve the issue. Print corrected soil moisture to get export image to drive. This is a function typically we use to save the output into Google Drive, and then through the Google Drive you can download and bring it into your own desktop software. Couple of arguments necessary for the output. The first is the image you want to get export. This is corrected soil moisture images that is stacked into a single TIFF file, and clipped based on region of interest, that here is geometry. The description refers to the name of output TIFF file, that is soil moisture with 1 kilometer that is corrected. And the target folder you want to save in, for example, in my Google Drive is test, but you can choose any other name for the target folder. The region of interest for the output will be geometry. The scale or the pixel size will be 1000 meter, and the CRS, the coordinate system, equals to EPSG 4326. This is WGS 84, that you can use this coordinate system for all around the world. Now, these are the main arguments that are necessary for getting an export or to save your data to Google Drive. So, as you can see, the corrected soil moisture is calculated and ready. So here, as you can see, we can do visualization for this product and compare it with 9 kilometer data. So here, map.add layer can help us to do this process. Map.add layer. So a couple of arguments here. Replace the first one with corrected soil moisture, 2 bands, stack them into a single TIFF file, and clip it based on the geometry. No need visualization parameters. And the name, the previous one was SM 9 kilometer, the new one with SM 1 kilometer, and turn the shown as a false, turn it into a false to avoid automatic visualization. As I mentioned earlier, it reduces the speed of processing, but the false helping us to avoid it. Run the code again. Once the new image calculated, we can do visualization. Wait until image collection is done. So here in the task also, we have soil moisture with 1 kilometer that is corrected. It is ready to save in the Google Drive. So you must wait until image collection is done. You can try for the save and also save in Google Drive, and also you can try for the visualization. As you can see, now we can do the visualization. It's a little time consuming because this is an output of a model, but same time I can click in run to start the process of saving into the Google Drive. But I got an export, and also that will be useful if we had any problem for the time of saving or anything like that. So here we will have the corrected bands. For example, the January 2023 with 1 kilometer is available. I'm increasing the contrast with 90% of values. Once the range of values updated, I can click on apply to see the final values and final image. Until it's done, here I can show you, for example, instead of a small random forest, also you can use the other methods such as gradient tree boost models. That is also another useful regression based technique that we can use for this purpose, and also it is also one of the best one that you can use for the downscaling. The image is ready, and then click on apply and check it on and wait until the final image loaded. I'm doing zoom in. This is the satellite view. You can see the corrected image also is in progress. Whenever you do some sort of modeling, such as we did, definitely the visualization in the Google Earth Engine for its final results will be a little will taking a little time, and that's why I'm suggesting to get an export from these outputs and check them into the desktop softwares. For example, I already did this and also got the export, and it is available in the Snap software that I can show you here. This is the final data that is downscaled for the region of interest. This is the region of interest that you can see shows the soil moisture values with higher spatial detail for the region of interest with 10 days interval. As you can see, 37 bands is available, and also these regions with agricultural activities, we have actually the higher soil moisture, and the regions without vegetation covers lower vegetation covers, lower soil moisture values. And here you can see that it is calculated and available, and you can see the final result here. Yes, and also you can compare it with the original image. The original image, yes, there is. In the Google Earth Engine, visualization is a little difficult unless you use the other regression techniques that are simpler. For example, now I'm going to try with a gradient tree boost method and run it again to see that how it works. It is also a powerful method and also taking a speed of processing same as the small random forest. No matter which kind of methods you are used, but the only thing is matter, the small gradient tree boost and also the random forest, both of them are a part of the best methods that you can use in the Google Earth Engine platform to improve the spatial details and also the downscaling process. For example, the new result is with 1 kilometer resolution. I'm waiting for coming up options first, and then doing the visualization. And the output is still under computations, but the process is done, and also you check that you can see the final result will be like this, and also the code is also available, and you can use it for your own studies. And also I have already mentioned about the reference paper. If you want to use this code, if you want to use this strategy for the soil moisture downscaling process, you can reference to this article, and also its code is also available in this tutorial. The code link is below the video on my YouTube channel. You can find it and try for your own study area. If visualization in the Google Earth Engine, same as what I have here, is a little time consuming, the best plan is getting export from the output and opening it up into the desktop softwares. And also you can compare the results of different models, random forest, gradient boost, and also you can compare the different methods to get better understanding about the methods applicability and efficiency. If you had any problem and issues regarding the codes and technique, you can reach me out on my YouTube channel and asking your questions. And also you can also share your link, share your codes like this using this link available here. You can get link from your code and share it with me on the comment tab and asking me questions. Then I can see your codes immediately, and this way helping me to get better understanding about your situation and helping you to solve the issues. And also this is the result for gradient boost method that you can see. Increase the spatial detail very well, and this is the code that's showing you how to get export from the output. Thank you for your attention. I hope you like this tutorial. Please reach me out on my YouTube channel and ask your questions, and also give your suggestions for the next tutorial that is necessary in the earth science studies. Thank you for your attention.